into class, but I mean, these videos are not great. They're not great. So, and it's kind of annoying to watch a super long video. So, so I hope you will continue to come to class, but if someone's gone, I'll try to live stream. Okay, well, that should be good. All right, so who's missing today? I guess whoever didn't have an exam up to. So Alex, Zoe. All right. So where were we when the power went out? We were doing the proof of the fundamental theorem of arithmetic, and which is, let's see, what do we call that? Theorem 1.8. And I don't remember where we were in that proof. Okay, so we were just writing what we were going to need to use, and okay. So so let's kind of fly through this proof. Okay, so you all have the theorem written down, right? So I'm not going to rewrite it. We'll just go on from there. So here's the proof. Every integer except 0 and plus or minus 1 has a prime factorization by theorem 1.7. So we've already proved that there is a prime factorization. So we're going to assume that it has 2 and then show that the 2 are actually the same. Okay, so that's how we do the uniqueness part of this. So, so let's suppose that, let's say n equals P1, P2 to PR, and n equals Q1, Q2, QS, that's an S, for PI, QI primes. So we have these 2 prime factorizations. And, you know, we've seen this before, right? We've seen that, like, for instance, 35 could equal 5 times 7, is that right? Yeah. But I could also write 35 is -5 times -7, right? And so what we want to say is that those are essentially the same prime factorization, right? So they're so what we're trying to get at is that the P1 is equal to plus or minus Q1, P2 is equal to plus or minus Q2, and so on, right? So that's what we're trying to get at on this uniqueness bit. Okay, so what we get is that P1, P2, and so on, PR is equal to Q1, Q2, and so on, QS. And so what we have here is we have these 2 lists, these 2 primes multiplied together, and we don't even know that it's the same number of primes, right? So that's why we have 2 different letters here for the R and the S. But we did have a theorem that said that if a prime divides some number, some product, then the prime must divide one of those, right? So that's theorem or corollary. What was that? Corollary 1.6. Since P1 divides Q1, Q2, QS, then P1 divides one of the QI. Okay, QI, yeah. So let's relabel and reorder so that that QI is equal to Q1. So we're going to just whatever one it divides, we're gonna move that one to the front. That's what we're gonna do, okay? We're gonna relabel, okay, so maybe I said that weird. So the QI is the first one. And we're gonna call it Q1, and we'll, whatever used to be Q1, we'll give it a different name, right? Okay, so then we'll have that P1 divides Q1. But since they're both primes, what does that tell me? What kinds of things can divide Q1? Q1 is prime. And what does the definition of prime tell me? What can its divisors be? What are the divisors of Q1?
Just one.
One plus or minus one and plus or minus Q1, right? So if P1 divides Q1 and P1 is prime, it's not it's not plus or minus one. P1 is not plus or minus one, is it? Because it's a prime, okay? So the only possibility is that P1 equals plus or minus Q1, okay? So let's write that all out. Since Q1 is prime, we have that the only divisors of Q1 are plus or minus one and plus or minus Q1, right? Since P1 is not equal to plus or minus one because it's prime, we must have that P1 is equal to plus or minus Q1. Okay, do you follow? And then we do this annoying thing where we continue in this manner, right? that's going to be what we're going to do. So we're going to get this. We're going to get that that P1 is plus or minus Q1. So I'm just going to replace P1 with plus or minus Q1, P2, P3, and so on. PR equals Q1, Q2, QS. Well, then I can divide both sides by Q1. And I get plus or minus P2, P3, PR equals Q2, Q3, QS. So now I've got the same sort of statement that I started with, right? So I'm going to do the same thing. So P2 divides one of the QIs. Reorder and relabel, right? Reorder and relabel. So that P2 divides Q2. Then P2 equals plus or minus Q2, and so on. And we're going to do that the same way. So we're going to like kind of slough off every one, right? Starting from the beginning. We'll take off the P2s, then we'll get rid of the P3s and Q3s, and so on. Since this is a finite list, that process will eventually end, right? But we have to deal with the case that R might be different from S, right? So we're not sure which one's bigger. So we'll deal with that fact and then we'll be mostly done. Okay, so okay, I'm on the wrong page here. Okay, so we can do this by contradiction. So we want to show that R and S are equal to one another, right? So we continue in this manner. And so on. So then we'll assume that R is greater than S. So assume that R is greater than S. Then we'll take off everything up to S, right? And we'll be left with PS plus 1, PS plus 2, and so on up through PR is equal to 1, right? Because I've divided all the Q, everything, all the Q's away. And I just have these leftover primes on the right-hand side because R is greater than S. Does that make sense? Okay. So what does that mean? Where's my contradiction going to come from? So if there are more primes on the right-hand side, well, what must be true of these primes? This prime must do what? It must divide 1, right? Does that make sense? So P S plus 1 must divide 1. So we're going to get that. Okay. So P S plus 1 equals plus or minus 1. But for the definition of prime, it had to be a number that was not plus or minus 1, right? So, so P S plus 1 is not prime. And there's my contradiction. Okay. There's my contradiction. And we'll use a similar, we started by assuming that R is greater than S. We could do a similar contradiction if we assume S is greater than R, right? Thus, R equals S, and the QI is equal to, or PI is equal to QI plus or minus QI, or all, what do we assume? R equals S, so we'll call it R, which equals S. Yeah. So, sorry for you online people, I'm moving. All right, good. Yeah, so I said this group is kind of boring, but anyway, we have to deal with the uniqueness aspect. So anytime you're doing a uniqueness proof, you just assume that there are 2, and then you have to show that they're equal in some way, right? So we assumed that we had 2 prime factorizations, maybe possibly of different lengths, right? We started showing that this P is going to divide that bunch, which ends up meaning that P1 is equal to plus or minus Q1. And we can keep going, we'll get P2 equals plus or minus Q2, and so on. Then we have to deal with the length of the string of primes there. We assume one side's greater, has more primes than the other side. We get that those primes divide 1, which is contradiction. Same thing the other way, and that's it. Okay? All right, so that is basically the end of section 1.3. So we've done pretty much everything in that section. So section 1.3 homework is homework 10 and 11. So at this point, you should be able to do homeworks 10 and 11. Do you have any questions from homework 10, which is due tomorrow night? Do you all have a chance to look at it? Some of you have already turned there. Yes.
Didn't you say that you just want us like, you have all those primes, didn't you say like we just need to look them up?
Yeah, just look it up. That's fine.
Like for the Euclidean algorithm, do you want us to like actually write it out?
Yes. Yeah, so write out the Euclidean algorithm for sure. In fact, I should have had you do the Euclidean algorithm and then write them as a linear combination. Like remember the back substitution thing from the, but I didn't ask you to do that. But I should have done that because it's it's good practice to try that out. So yeah, so that's homework 10 and 11. And then homework 12 is going to be all about induction. So we're going to skip over to Appendix C now. And we're going to do induction. And we probably won't finish induction today. We'll probably leak into Friday. And then we'll be kind of done with chapter 1 and appendices A through C. So we are rocking and rolling and moving along here. So, okay. So let's start with appendix C. Oh, did I leave my notebook in the office? I think I did. Okay, hang on, I'll be right back. Yes, ma'am. Sure, yeah.
On the first part, where you want us to like express the numbers as like positive prime, do you want us to show it like, if the numbers are positive numbers, do you want us to show it, I don't know, like 16 times something, 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 do you want us to also do it negative? Like,
No, I don't care. No, no. Yeah, you don't have to show every possibility for a particle prime, just one,
Okay,
yes. And they don't even have to be in order, really. I mean, like, when I did it in order because, you know, I just have to. But yeah, but you don't have to put them in any particular order. Okay. Yeah, so I think problem 1 is expressing a number as a product of primes. So you just have to find its prime factorization. 1.3.2 are asking some questions about primes of the form 2 to the n plus minus 1. So those are some. That form of primes shows up from time to time, but anyhow. And then some question about, are these numbers prime? And here's a list of numbers. So you just have to figure out if they're prime or not. And then listing the all of the twin primes up to 200. Okay, so you can use the Googles on that. And then reading the proof of theorem 1.7, which we have already done, and talking about the purpose of that set S. And then using the Euclidean algorithm. So it's pretty computational, homework 10. So it should be not so bad. And then there are a couple more that are not so computational. So 1.3.6 actually, and 1.3.7 are actual proofs. So yeah, but they're pretty straightforward, I think. Yeah, so homework 10 for tomorrow night, and then homework 11 for Tuesday. I'll deal with stuff from section 1. All right, so on to the next thing. I should have brought dominoes today because we're going to talk about proof by induction. But if you remember back when we started on maybe one of the first days of class, I said that something is equivalent to proof by induction. Do you remember what it was? Well ordering axiom. Yeah. So the well ordering axiom is an axiom. Oh, whoops. Always forget. Oh, okay. So the well ordering axiom is an axiom, which means it's something that we assume to be true, right? And that's equivalent to this idea of proof by induction. So, and that's proved that there's a proof of that in Appendix C. I'm not going to go through the proof of it because I think it's kind of boring, but those two things are equivalent, the well ordering axiom and proof by induction. So let's write down the well ordering axiom. So y'all should have this memorized. What's the well ordering axiom say?
For every set of non-negative.
Good, yeah. So I'll say subset of non-negative integers. Oh wait, I forgot non-empty. Contains a smallest element. Okay, and again, this is not true of the real numbers, say, okay, because do you remember talking about this? Can we create a set of real numbers that does not have a smallest element? Yes, what? Like
all of them, including the negatives.
Yeah, so, okay, how about of the non-negative? How about of the non-negative real numbers?
Just the.
What, an open interval? Yeah, that's the idea. So something like 0 to infinity does not contain a smallest element. There's not a smallest element in there, right? Because I can keep getting closer and closer to 0. And if I assume that I had a smallest element, well, let's consider that element divided by 2. So we had this conversation before, but so this property really has to do with integers. It really has to do with non-negative integers. So it doesn't necessarily work for any set of numbers. Okay, and so here's our consequence of that. Is the method of proof by induction. Okay, so it's the method of proof by induction. So this can be used to prove statements involving the natural numbers. Marker is speedy. So the method of proof by induction can be used to prove statements involving the natural numbers. So it has to be involving the natural numbers because we were saying that the well ordering axiom is really specific to integers, right? Positive or non-negative integers. Proof by induction, again, is specific to natural numbers or non-negative integers. Okay, so we have to have a statement on that. So here's an example of a statement about integers. So we could say a set of n elements has 2 to the n subsets. So that is a statement that is based on the integers, right? So I'm going to give you a second to process that statement. So I want you to think about this statement with your group mates and just kind of process, what does this statement mean, right? So think of some different, maybe some sets, some finite sets. These are finite sets, a set of n elements. And then what are the possible subsets of those sets? And that way we can just kind of process what this statement is saying. So take a minute and do that.
There's just a set of elements that are that makes it up. So and the subset. Like it's made of those elements, so it's either going to have one of those or it's not. So like yeah, you can like the size of my fingers, right? Any subset of my fingers is either going to have the finger or not, right? So it's just on or off. So you can do like you have two choices for the first element, like in five. You have two choices for the second. Yeah, you don't have and then there's two sets. Yeah. I mean, like you look at the medium set this subset. Right. Yeah. So, actually, there was an interesting part of the textbook. I think it was in the appendix. It wasn't super important, but they explained how, because we take the convention that a false statement, like the whole statement, false implies true. We have a convention that that means true. You can prove from that that the empty set is a subset of every set. So, yeah, so you get.
Okay, so questions about this. I heard some discussion about the empty set. Yeah, what was the discussions about the empty set?
We were just saying it has to be a subset.
The empty set is a subset of any set. Yeah, so that's true. So that's something that we're going to need for this. Right? Other thoughts about this statement? You believe it? Yeah. Okay. What makes this statement believable to you?
We said that if you have a set and you want to generate a subset of it, every element of your subset is either it's going to include something from the original set or it's going to exclude something. So it's either gonna be there or it's not. So for the first element, you can either take it or leave it. So, and then the second element, you can take it or leave it. Third element, you can take it. So you have two choices for the first one, two choices for the second, two choices for the third. And so for all the elements, you just get two more choices, so 2 times 2 times 2.
Does that make sense to you all? How that works? Okay. Yeah, and so that is definitely a way that you could prove that, right? That way it doesn't involve induction. Well, maybe you could use that thinking with induction. But yeah, so when we talk about induction, we want to think about that any statement about the integers is actually infinitely many statements, right? All in one. So this statement has, so the notation that we're going to use is like P0 will be the statement when 0 is plugged in for n, right? So P0 says that a set of 0 elements has 2 to the 0, which is 1 subset. Okay. So a set containing 0 elements has 1 subset. And what is that 1 subset? The empty set, right? That set is the empty set and its subset is the empty set. So not only is the empty set a subset of every set, but the set itself is a subset. Okay, so both of those things. And then we could have another statement P1 that says a set of 1 element has 2 to the 1, so 2 subsets. Right. So if it's the set of 1 element, a singleton has 2 subsets. So there's the set itself, the singleton set, and then there's the empty set. There are 2 subsets of that set. So do you see how I could generate infinitely many statements from this one statement? So this statement is a statement about all the integers, but it has, all of these infinitely many statements. Okay. So that's going to be important as we start to think about proof by induction. So let me give you the statement of the principle of induction. And then we also have strong induction, which I'm not going to emphasize a whole lot here, but that's another version of the induction statement. But it's in the appendix too. So, all right. So the principle of mathematical induction. Okay. So we say that assume that for each non-negative integer n, a statement Pn is given. Okay. And then we say if we have 2 conditions. 1, P of 0 is a true statement. And depending on the statement, sometimes we'll use P of 1, right? So in other words, we want to say that this is the first one is true. Like we have to show that the first one is true. So this we'll call the base case. So this is the case for the smallest n that we're considering here. So some of the statements that we're going to talk about start with n equals 1 and so on. And some of the statements start with n equals 0. So it kind of depends on the statement, what our base case would be. Okay. And then the second thing that we have to show, and this is called the induction step. So is that whenever PK is true, then PK plus 1 is also true. Okay. And so this is called the induction step. So to then the statement Pn is true for every non-negative integer. So to show that it's true for every integer or for every non-negative integer, we just have to show that that's true for the first one, right? It's true for the first one. And then we show that if it's true for one, then it's true for the next one, right? And so then that will knock out all of the integers. And so the way that this works is kind of, I think about this like dominoes, right? So if you knock over the first domino, it knocks over the second domino. The second domino knocks over the third domino, and so on, right? And it'll knock out, it'll go through all of the integers by proving this step. Okay, now we've got to do some examples using it. So here's an example. I put an easier one that's kind of like this on your homework, but a lot of you have seen these types of formulas before. They show up in calculus 1, really, when you're doing a Riemann integration, and you have to show that the limit of the Riemann sum is the integral and so on. So we're going to show this this statement is true. So 0 squared plus 1 squared plus 2 squared plus up through n squared is equal to n times n plus 1 times 2n plus 1 over 6. Okay, so have you seen this formula before? This expression before? Okay, you did it back in calculus 1 at some point. Well, you might not have taken calculus 1 in college, so maybe you didn't do it. Anyway, so there's a similar one for just adding the first integers. So if we say 1 plus 2 plus up through n, you know the formula for this one?
Times n plus 1 over 2.
Yes, so it's n times n plus 1 over 2. And this is a famous one. There's a story that goes with this one, that the mathematician Gauss, when he was a little boy, his teacher was trying, well, so, who knows if this is actually true, but this is the way the story goes. So the mathematician Gauss, when he was a little boy, his teacher was trying to just keep the kids busy, right? And so he said, sit down and sum the numbers 1 through 100. And so immediately Gauss walks up and puts the answer on the teacher's desk that it's 5,050. And so the method is you can pair n plus 1 and you get n plus 1, and then you pair 2 and n minus 1, you get n plus 1, and so on. Oh, well, he was doing 100. So you pair 1 and 100, you get 101, 2 and 99, 101, and so on. So that's, and then you get 50 pairs of 101, so that's 5,050. So that's his little proof of that. I'm gonna have you do this in the homework, but not with that method. You're gonna use induction to prove this in the homework. So we'll do an example with this one, and then this one will be really easy once you've done this harder example. Okay, so anyway, yeah, I had to tell that story to my friend, because my friend Sarah has a orphanage in the Congo that her family runs, and she was doing this thing where she was asking people, she had 100 envelopes, and she was asking people to donate, like the first envelope was $1, the second envelope was $2, up to 100. And she totaled them all up and got 5,050. And her daughter was like, that doesn't sound right. It should be more even than that, And I was like, no, here's this great story. It's I got to tell her the whole thing. Anyway, I'm not sure that my friend appreciated it, but her daughter did. So there's that. Anyway, okay, so let's prove this guy by induction. So we're gonna do the proof. And we'll say by induction on n. And I want to be specific here about what I'm doing induction on. Now, this statement only has one variable, but we'll talk about some other statements that have multiple variables going on. So you want to kind of say, like, what are you doing induction on? Like, what's the variable you're considering going through? So this principle of induction is actually going to be a formula for how we're going to write the proof out. So we're going to do it in 2 steps. And so we're going to say, so we'll say the base case. We're going to assume for n equals 0. Well, I have on the right hand side, I have 0 squared. On the left hand side, I have 0 times 0 plus 1 times 2 times 0 plus 1 over 6. Well, that's both of those are 0. So it checks out. So the base case is usually boring, right? So it works for the base case. It works for the first number we're considering. So I just put a little check mark there. So I don't know. But then induction step. If you want to be better than a check mark, let's say this. Say we can say so P sub 0 is true. That looks a little more formal than my check mark. Okay, good. Then the induction step. So for the induction step, I want to prove that if PK is true, then PK plus 1 is true, right? So I want to, this is an if-then statement. I'm going to do it directly. So I'm going to assume what? I'm going to assume PK is true, and then I'm going to use that to prove that PK plus 1 is true, right? So we're going to assume, well, what is the statement PK? Well, it would just be that with K plugged in, right? So we're going to assume that 0 squared plus 1 squared plus up through K squared is equal to K times K plus 1 times 2K plus 1 over 6 is true. Okay, and then I want to say something about PK plus 1. So I'm just going to assume that that's true. And now I'm going to start to say something about PK plus 1, but I need to use that fact in my, as I go along, right? So that's what I'm going to do. So what would the statement PK plus 1 be? Let's just go over here and write down, what is the statement PK plus 1? This is where we're trying to get. So what is that statement? Well, that statement is 0 squared plus 1 squared plus K squared plus K plus 1 squared, right? Is equal to, now I'm going to plug in K plus 1 for n. So I'll have K plus 1 times K plus 1 plus 1, right? Times 2 times K plus 1 over 6. So that's the statement PK plus 1. This is what I'm trying to prove. Okay, so I'm going to try to prove this. I'm just setting this over here to the side so we can remember that that's where we're going. We want to get to there. So how do I prove that this is true? Well, I'm going to start here, and then I'm going to use my facts to replace part of it, and then I'm going to do some algebra. So that's what we're going to do. Okay, so we'll say 0 squared plus 1 squared plus 2 squared plus up through K squared plus K plus 1 squared equals, and I'm just going to have a long string of equalities as I do all this algebra, okay? Well, what can I do? I can replace this first part with what? I know what that's equal to, right? So I can replace it with that. So I get K times K plus 1, 2K plus 1, all over 6, plus K plus 1 squared. Okay. What does your gut tell you to do? I want to get this, I want to manipulate this algebraically until it looks like that. I want to try to get to there. That's where I'm trying to go. Colin?
Do we have to multiply everything out?
We may. We'll try to avoid that as much as possible. We'll have to do a little bit of that. I only know that because I already did it, but yeah. So what does your gut tell you to do first? Common denominator, yeah, common denominator. So we'll put this, multiply this by 6 over 6. So we get K times K plus 1 times 2K plus 1 plus 6 times K plus 1 squared, all over 6. Okay, now what? I'm not multiplying that out. What else could I do? Colin?
I can't see immediately if this would work, but could you like, I guess we technically have to temporarily leave the integers for this, but could you change the variable so that you can write K times K plus 1 as K minus a half times K plus a half? Or like a different letter, I guess, but like.
Oh. I don't know. So you're doing a change of variables.
Yeah, just so, because that way you'd have a difference of square, and then like the K plus 1 squared would be like T plus a half.
Oh, maybe.
And maybe
I'm
the
not
bottom.
certain that that's going to be a productive way because I haven't thought it through all the way. So maybe that would work. I'm not sure. But there's something we can do without changing the variables. Can you see it? You see, Peyton sees it. What do you see, Peyton?
Well, K+1.
Pull out a K+1. There's a common factor. Right. So there's a K+1 here and here. So I'm gonna pull that out of both of those. So I'll have K+1. Oops, and then what's left in this first is just K times 2K+1. And in this one, I'll have 6 times K+1. Maybe I'll put brackets so it's really obvious what I've done here. So I pull the K+1 out of both of those two terms, and then that's with what they were in both of those terms. Now multiplying that out is not so bad. It's just, that's not as bad as multiplying that out before. And look what I've got here. I've got a K+1 factor in the front. Is that good? Look over where I'm going. Yeah, I want that. I want a K+1 factor in the front. So, so all that's over 6. So now I can do what? I'm going to multiply it out. So I'll have K+1. How are we doing on time? I haven't even looked. Oh, okay. And then I'm going to multiply that all out. So I'll have 2K squared plus K plus 6K. So how many K's is that? 7K? Okay, all over 6. And then, oh no, that's not a 1. So I multiplied the 6 by 1, so I get 6. Sorry. Okay, and then does that factor? Okay, how does it factor? Well, factors of 6 are 2 and 3, right? So I need to put a 2 and 3 here and here, but I need to get a 7 in the middle. So if I do a 2 here, that gives me a 4, and a 3 there will give me a 3. So that works. Okay, and everything's positive. Okay, and so is that what I wanted? How close am I? Now it's just making it look right, right? So K plus 2 is the same thing as K plus 1 plus 1. And 2K plus 3 is the same thing as 2 times K plus 1 plus 1. So PK plus 1 is true. That's the statement is proved. Okay. So that's the method of induction. And so on Friday, we'll just do 2 more examples, and we may end early on Friday. Would that be good? So there's an example of induction. We'll do a couple more examples. And so what I have planned for you on Friday, I think you'll be excited, is we're going to prove your very favorite theorem, the division algorithm. But instead of using the well ordering axiom, we're going to do it using induction, because we've said that the induction is equivalent to the well ordering axiom, which means that everything we prove with the well ordering axiom could also be done by induction. So, so that's what we're going to do on Friday, is we're going to prove the division algorithm using induction. And so you are probably thinking, induction on what, right? That should be what you're thinking. Because I was saying before, now here it was easy. I only had one variable. I was doing induction on n. But the division algorithm, there are so many variables floating around. So you should be thinking, induction on what, right? Well, I won't spoil it, but we'll see it on Friday.
I feel like it would have to be R, right? Because that's what
Well,
originates.
some of you might Google it before. Now, how do I stop this? Do I just?
Did you get it? Yeah.